Hello, I'm Josh. Thank you for clicking on my YouTube video. And I am going to show my Voxel planet. In the last video, the planet was just a sphere built using Bevy's mesh builder. And now it is a sphere with mountains composed of a 3D grid of cells. And you can dig into it, you can dig into the dirt, you can dig a tunnel, a cave, whatever it is, and also shoot little lights out. And it's pretty cool. And so I just want to show what it looks like and how it works. So let's... Okay, and we are falling down onto the planet. As you can see, it looks a lot different than it did last time. I'm gonna go ahead and get out of the mountains here. So last time, I implemented gravitational physics, and that is still in place here. So I can take off if I put on my jetpack and go into orbit around the planet, and I will be able to circle around the planet indefinitely without ever applying any more forces. And I'm always pulled toward the center of the planet. But now, as you can see, I've added some terrain, some mountains. And the flat ground here does look a little bit bumpy. Making it smooth is trivial, but the reason I left it bumpy is because, long story short, when I made it perfectly smooth, I ended up with large gaps under the mountains, which looked a little weird. So I have yet to tweak the noise generator function that produces this terrain. But for now, I really just want to show you that I can terraform this mountain and that it was produced using random noise. So here we go. I'm gonna go ahead and click into the mountain. You can see I can dig into it and it just kind of melts away. And then I can right click and my brush just sort of produces more ground. Also, I can dig pretty deep into the earth here. And as you can see, it looks a little hard to see what's going on, but if I hit Q here, I can just drop a little light ball and it rolls around. And I think that's pretty fun. And I can dig all the way to the center of the planet and even to the other side. There is no limit here. I can just kind of keep going and I can launch a bunch of light balls down there. And as I get closer to the center, I'm sure you can see in the upper left-hand corner, the gravitational pull on me. Whoa, I just flipped because I just went through the center. But the closer I get to the center of the planet, the less gravity I experience, and that's called the shell theorem. The way gravity works to begin with is all particles pull on each other all at once, and they have a stronger pull when they are closer to each other than when they are far away from each other. However, if you think about it, when you're in the center of the planet, every particle on the entire planet is pulling on you all at once, just like when you're on the surface, except since you're in the center, they're pulling on you from all directions all at once. And so it's sort of like experiencing 0G. And as you can see, the balls in here are also experiencing zero gravity, very similar. So anyway, I just thought that was a pretty cool feature. This is something that you also see in other space games like Astroneer and Outer Wilds. So now I'm gonna go ahead and try to get out of here. A little bit dark. I'm just gonna keep digging. So this would be the other side of the planet that I spawned from. So I think one of the ideas here is that you could, make a little cave, call it your home, spawn a little light orbs in here and light it up. It's been pretty fun just to kind of play around with a little bit. I'm now gonna go ahead and go into a technical section where I will talk a little bit more about how I accomplished this. So to explain how this marching cube algorithm works, I have this example I threw together in Bevy, and you can find the source code for this in the description. Please do try it out. It's very fun to play with. And when I click on these dots, you can see it just builds a mesh or a bunch of triangles. And this is how the surface of my planet is built. And just to be clear, whenever you see a square like this is actually just two triangles behind the scenes. But what do these triangles mean? Well, the red dots are supposed to represent points below the surface of the ground, and the white dots are supposed to represent points above the surface of the ground. And as you can see, these two dots are below the surface of the ground, and it looks just as empty as these two dots. And that's because that's all the planet really is it's just a mesh or a bunch of triangles that are put together to look like the surface of the ground. So let me take a step back and explain a little bit more about how this is working. I'll go ahead and turn all of these off, and we'll say this whole cube is underground. And now I'm going to click this dot here, and we'll say, okay, well, this cube is above ground. Now, what we're looking for when we're building the mesh is we're actually looking for where underground meets ground. So if we compare every single value with its neighbor, then we can find where this surface is. So for example, these two dots here, we'll compare them. They're both underground, so there's no surface. These two dots, they're both underground, there's no surface. These two dots, one is underground and one is above ground. Therefore, there's a surface. So we're going to mark this edge here, and the edge is invisible, but by edge, I just mean an imaginary line between these two dots. This edge is an edge we're going to draw a triangle from. One of the points of the triangle is going to exist on that edge. Then we keep going. Between these 2 points, one is above ground and one is below ground, so we're going to mark this edge. And then finally, the only other edge is this edge right here. Now, as you can see, we have 3 edges where below ground meets with above ground. And now all we have to do is connect these edges to form a triangle. And that's exactly what you see here. We take the middle point of all of these edges and just connect them together. And if we start adding more cells to be above the ground, you can see the algorithm stays the same. We're still creating a point on every edge that connects a point above ground with a point below ground. And we can form some really interesting and complex shapes like this. Now, you might be thinking, well, if you connect a whole bunch of dots together, how do you avoid getting holes or gaps when you connect this cube with another cube? Well, the thing is, this sort of works itself out because these 4 points here are actually shared with the cube next to it. And so you'll never have a conflict because this point is this point is below ground for both this cube and this cube. Allow me to demonstrate. Here we have a grid of 2 cubes by 2 cubes by 2 cubes. And if I just start picking points here, you can see I just selected one point to be above ground, which is funny because it's in the center of the cubes. But still, it's going to draw the same triangle that you saw earlier, but in every single cube. And then we can start combining these together like this and form all kinds of interesting, unique shapes. As you can imagine, you can get really creative with this. The entire planet that you saw earlier is just a huge grid of these cells. And I have flipped some on and some off to indicate under the ground and above ground. And I've also used a random number generator to create mountains, and I can use it to create caves, and I can do all this because all of the terrain is just defined by values assigned to cells in a grid like you see here. So as you can imagine, this can start to get really computationally expensive. Just to make the planet that I showed you required almost 600 million cells. That's a lot. And the planet that I showed you is also about 1/10 of the radius that I actually want to have my largest planet be in the final game. Which does not mean I need 10 times more cells, by the way. That means I need 10 times more cells per axis. And there's 3 axes, so that means 10 to the 3rd power more cells, which is 1,000. That means instead of 600 million cells, I need 600 billion cells. So in order to tackle that, I need to optimize a lot. And this video isn't about optimization. I have a video coming out for that. But one small optimization that I have done to make even that planet possible is to chunk it up. Or in other words, to split up all those cells into chunks of cells. And so you can think of like Minecraft. Each chunk has a certain number of cells in it, and I can process all of these chunks simultaneously. I do not need to process each cell one by one. Instead, I can process one chunk on this thread and another chunk on this thread and another chunk on this thread. They can all be working independently of each other. And so this has sped up the process quite a lot, and I can show you what that looks like right here. So I have enabled chunk highlighting, and what that does is it just draws a pink box or pink wireframe around each chunk, just so that we can visualize what chunks look like. I'm gonna go ahead and fly here. So as you can see, a chunk is about this size. Right now they're about 32 cells by 32 cells by 32 cells. But as you can see, I can terraform even on the boundaries of the chunks, and it works just fine. Well, I hope you enjoyed the video. Thank you so much for sticking around. That's all that I have to show you today. Next time, it is going to be about performance optimization, because I need to try to target a planet that is 10 times the diameter of that planet. And then shortly after that, I will probably target making interesting terrain, as I just threw that terrain together. I don't actually have any idea how it works right now. That'll be something I need to dive into. Thanks again for watching, and bye.